Well, thank you for this nice presentation. Of course, my talk will be not on the motor cortex, as was announced before, but will be on the mirror mechanism. I will talk also about the motor cortex. Well, let's imagine that that's a scene. You are in a bar, and you see somebody grasping a glass of water in this way, or maybe in this way. So what do you understand? You immediately understand the action, grasping, but I think all of you understood it if I grasp like that. It's completely different if I have grasped it in this way. That's for drinking, that's certainly not for drinking. Well, how we explain all this stuff that I just mentioned? So according to classical point of view, what I do, I describe inside my brain the shape of the glass, the hand, and then I do an inferential process. I somehow mentalize and decide that what I did or what the guy did in the bar was grasping. If you think, so in this way, grasping an object, an action done by a person, is the same thing as another type of understanding, like a physical thing, a body falling down. Traditionally so, the analytic philosophy considers that's the way in which you understand things. However, there was an alternative point of view, which has been proposed by phenomenologists. Husserl, of course, was the head of them, their most important philosopher, but Merleau-Ponty maybe was the person who better explained the concept. If you see, he says, the sense of gesture is not given, but understood, that is recaptured by an act of the spectator part. The communication or comprehension of gesture comes about through the reciprocity of my intention. So in other words, I understand you, or the guy in the bar, not in the same way as I understand things happening, but I understand because I attribute to him some particular properties which are proper also to myself. So he's a person, he's not a thing. Instead, when we understand the law of physics, there is no necessity to think that there is a person there. So it's not a small difference. The way in which we understand other simply is other things, in the infinite things that are in the world, or I understand the person because they are person. So as I said before, the point of view of phenomenologists, although it was rather popular in France, maybe also in Germany, but certainly not in the United States. If you speak with Dennett or other philosophers, they will say, that's nothing, that's just poetry. Well, as a matter of fact, I think there is a mechanism which explains that this point of view, to understand the other as person, it's true. That is present also in monkey, not to speak about apes. Well, it's called the mirror mechanism. Before speaking about mirror mechanism, I have to spend a few words in physiology, because I am neuroscience. Before we were a philosopher and so on, but neuroscience has to be explained a bit. So we recorded from the motor cortex, and somebody can be surprised that I talk about empathy and so on, but let's start with the motor cortex. In the last 20 years, our concept of motor cortex changed radically. First, motor cortex is made by several different areas, and they are indicated in color on the left side. So where it's written frontal 1, frontal 2, frontal 3, frontal 4, there is a mosaic of area. We approached the motor cortex using an ethological approach. So classically, the motor cortex was studied in purely physical terms, dynamic, kinematics. So actually, it was an arrogant point of view. So the science says, we know everything about motor cortex, it produces motor movements, but then let's see which are the physical parameters. Instead, we have an ethological approach. So we play it with the monkey, we give food to the monkey, we look at what the monkey does when throw away food, and so on, within limit of physiology. Well, one discovery was in the motor cortex, is called the goal of motor act. So not the movement, but the goal. So I will show you what it means by the goal. So that's movement. If I stimulate my cortex, I see here some movements. But if I do that, they are movements organized in such a way to reach a goal. That has been called motor act. So movement, it's individual elements, motor acts, when these individual elements are together in order to reach a goal. So from this neuron, you see that it's impossible to explain the motor course in terms simply of movement, because it's the same neurons which discharge. There are 3 histograms you see here. There are 3 histograms, and in one the monkey grabs with the right hand, with the left hand, with the mouth. So it's clear there is something more, but the goal is a philosophical concept. So when this neuron fire, there is the goal in the brain of the animal. It's not simply organizing the movement, but organize the movement in such a way to reach a goal. We have been challenged, and some people say, well, if you are right, let's use something strange like this instrument. Maybe somebody, I don't know if there's somebody, French people here, but you recognize that that's the instrument which in France is used to eat les escargots. I don't know why, but in France, in order to take snails, but it's working, it's working okay. I have the feeling it's going up and down. Anyway, if you use this instrument, if you think, it's a bit crazy, because in order to grasp, that typically we do like that, you open your hand. So instead of closing, you open it. So together with a postdoc from France, we did an experiment. First, we teach the monkey to use this instrument. Now, I want to show you that. So for those who are not acquainted with physiology, you will see the discharge of neuron. So the language of neuron is extremely simple. It's just frequency, tac, 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 tac. So if there is something really good, the frequency increase. It's modulation of frequency. So let's go back. Here is the instrument, and here is the... So you have to correlate the action with this tac, 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 which is the language of the neuron, action potentials. That's a grasping neuron. When the monkey grasps, there is a discharge. Just to show. Here is the instrument, I hope you see. Now the discharge is when the monkey opens it. You see here, she's moving, nothing, grasping, discharge. She's moving again nervously, she hopes to get food, there is no discharge. So this indicates the movement are not instrumental to determine the discharge, but it's the goal. Of course, we have better proof than that for the fact, because we record it using a potentiometer, but it doesn't matter for today. So, goal is present there. So when this neuron fire, they say the goals. They say grasping, they say pushing, they say moving, and so on. The other surprise was the many neurons in the motor cortex discharge when the monkey sees object. We call it now canonical neurons. So if you have a mirror neuron, you have a neuron which fire, for example, for this, let's call it precision grip. If you show a seed, there is already discharge in this neuron. In other words, there is sensory motor transformation, visual motor transformation. You see an object, and automatically you have in the motor cortex the motor program how to grasp it. If you have a neuron which fire for this type of, which is called whole hand grasping, if you show an apple, there will be a discharge in this neuron. So we have this kind of transformation. This was a very interesting discovery that we discussed together with Jean Ayrault, Michael Arby. However, it was still in the classical physiology. In a sense, it was predicted it should be this transformation in order to be fluent in the movement. The surprise was when we discovered mirror neurons. So in this case, as I said before, with Matelli, Gentilucci, with others, we studied these canonical neurons, and with the Japanese group especially. So was object presented. In some time, object was not sufficient, but if the person was acting, if the experimenter was acting on the object, was a discharge. That's from our old one of the first paper. You see in the lower part, the monkey is grasping, and you see this bar are action potential, and above is the experimenter grasping, and again the same action potential. The best way to demonstrate it, to show you a film. Again, it's very simple. You have to correlate this tac, 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 the discharge of neuron, with what monkey is doing and what the experimenter is doing. That's again a grasping neuron that you saw before. highly repeatable, no problem, every time. And here is the experiment they're doing on the same action. You see, it's the same goal. Inside the brain of the monkey, it says grasping. So this film is very nice because it showed first how it's constant. It's not an effect that we discovered because we did a lot of statistic histograms and then eventually the analysis of variance showed there is a difference and so on. Everybody can put an electron inside the brain of the monkey and see this type of effect. And monkey is not conditioned experiment. It's just our mind. As I said, we use this kind of ethological. So the monkey was there grasping food and we were grasping the food. However, it's not true, as was written in the New York Times, that one day one of us was licking ice cream and then the monkey started firing. It was not true. I mean, we were very careful, but certainly we were grasping food, giving to the monkey saw what we were grasping food. So it's not conditioned monkey. Now, what is the functional role of mirror neurons? Well, one can say that that's in physics they would say ill-posed question, because it's not that it's a function of these neurons. After the discovery we did, it has been found that mirror mechanism exists in our brain. So it depends where the mirror mechanism is related. If it's related, for example, in the insula, the neuron, or in the one we studied, the medial part of the brain, you can have a pain neuron for myself and for the observer. And if you are studying birds, Mooney in America did a beautiful experiment on birds, on singing birds, and they found mirror neurons. Same series of notes are emitted by the bird and the neuron fire when the bird heard the same notes. And so it's important where it's located. Here I summarize what I said before. So the mirror mechanism is a basic mechanism that transforms sensory representation into a motor format, and is localized in multiplicity of cortical areas in neural centers. And it has different functions according to its anatomical localization. And so we can now go back. What is the function of F5, of this first neuron that you studied? Well, I think, although there was a lot of discussion what can be the function, but I think from a physiological point of view, the neuron, we record the output of neuron. So it says always the same thing. It says grasping. So in one case, it says grasping because my will said grasping and then will be used for preparing action or for doing it. In other case, I see another person grasping, and in my brain, I have a kind of motor program which is for grasping. Of course, that's only logical explanation, so we did some experiment to prove it more formally. And one suggestion we received is, if this neuron really code the meaning of an action, we recognize, and monkey as well, the action also from the sound. So we did an experiment, very simple, in which we break, for example, a peanut or break a piece of paper, and the monkey either could see it or could hear the noise. So here is our protocol, very simple. So what you see here is many trials, and in the lower row is the histogram, and you see this bump, that's the discharge, where the monkey sees, what is that, paper broken into pieces. And here is the crucial point. The monkey doesn't see, but hear the noise and the neuron fire. So the monkey has the knowledge of what is going on. And here is a control, there is another noise, and nothing happens. So it should be that specific noise which the neuron code. This paper has been published in Science, so we were required to do population analysis and many complicated statistical stuff. Anyway, the result was very clear. If you look at S, sound, you see that the blue curve is much higher than red curve. The blue curve corresponds to the stimulus which triggered the neuron also visually, and the red is other type of stimuli. So at this point, it was a kind of mythology, saying, oh, well, when mirror neuron fire, we understand the thing. No, it's nothing magic in mirror neurons. When the mirror neuron fires, we have in our brain a motor schema which include premotor cortex, motor cortex. We have now data from London, Roger Lemon with Kraskov, shown that even in the corticospinal tract, there are a portion of neurons which are mirror. So you have the complete program to act, which is activated not by you, by looking at another person. So my program and your program is the same. Marc Janero, who was excellent writer, summarized it like that. The observation of action performed by other agents generate in the brain of the observer representation similar to those of the agents. This circular process from the self to action and from action to other self has a consequence that action representation can be shared by two or more people. These new findings have radically changed the traditional view of motor system as an executive system that merely follows instruction elaborated somewhere else. Well, that's the first part, this traditional part of my talk. On the left side are my group, which discovered with me mirror neurons, Luciano Fadiga, Leonardo Fogassi, Luciano Fadiga, and Vittorio Gallese. On the right side were the young student, the other were postdoc, the other very young students, which then also started to work in that. Some of them are well known, like Ferrari or Christian Kaiser, who is professor in Amsterdam now. Okay, now, if you want to learn something about the mechanism, you must use single neurons. But if you want to learn the circuit, there is other better method. And since 2005, we collaborated with Urban, who is professor in Leuven, and together with these other people, Nellis and Van Duffel, they made a very clever idea. So how to use fMRI, brain imaging, in animals. It seems very complicated, and in Tübingen they have a Max Planck Institute which have spent a lot of money making special mechanism and machine for that. In Leuven they have a very simple idea. If you condition a monkey to sit in this position, sphinx position, and fixate a dot, and occasionally the dot change color and the monkey has to press a button, the monkey stays for 40-45 minutes inside the scanner, and then it goes back to the colony. So for 40-45 minutes the monkey is still, and simultaneously we can present films. So we present these extremely boring films like that, but automatically it's encoded by the brain of the monkey, and we see which part of the brain is active during observation of action. And here is the data. I don't know what you can see, but anyway the important part is the lowest row, because it's 3 Tesla, the best machine, and there are 3 spots. One is in STS, superior temporal sulcus, which is higher order visual area, well known, studied in St. Andrews by David Parrott and by others. Then we have parietal lobe, and we recorded from parietal lobe, we found plenty of mirror neurons. And the third is the area I mentioned before, so premotor cortex, which extend maybe more rostrally. More recently, we did also with the same group a more sophisticated experiment, which I don't show into detail, but the result was that there are actually 2 streams. One is coming from the ventral part of this, you see this structure on the lowest side of the slide. So there are 2 banks, there are the upper banks and the lower banks. Both of them send visual information to the parietal lobe. Why that's important also for a talk like that? Because from scientific point of view it's very important to know which are the area involved. But also from the general public point of view, the ventral part receives also from infratemporal lobe. So in other words, this system knows the semantic of the object. So you can deduce not only the action, but also why this action is done because you have information about the value of the object on which the observer, the guy in the bar, it's grasping, it's a beer or it's something else. Now, somebody very critical can say, but really we need the motor system to understand action. You said they are visual area, very complicated. Why it's not enough? Well, one reason again is from Marc Généraux, which said a mere visual perception without involvement of the motor system would only provide a description of the visible aspect of the movements of the agent, but it would not give precise information about the intrinsic components, which are critical for understanding what the action is about, what is its goal, and how to reproduce it. So I don't know, if you play tennis, when you see playing Nadal or Federer, you understand much more if you have never played. So you understand what is the beauty of the play. And if you are a fan of soccer, I'm sure that when you see your team playing, you feel something in your leg when it's almost make the goal. If you don't care, it's crazy. People are running near a ball, what they are doing. Another point, which we think why the motor system is very important for understanding action, is something which we describe it, we speculated with Corrado Sinigalli, a philosopher. It's generalization. So when I said the same neuron fire grasping with the right hand and with the left hand, with the mouth, even with an instrument, I will show you in a moment also in humans, well, the visual system is unable to cope with this. The single neurons describe something, right hand or left hand or mouth, but they don't describe so many things which do the same goal. The goal is motor, it's not something visual. Well, that's the story about monkey. Then I will come back on emotion in monkey, but now let's move to humans. So virtually immediately we discovered in 92, but I was sure that we were correct 4 years later. For in 96, when we were sure that mirror neurons really exist, we started also experiment on humans. And we did what I already mentioned, so brain imaging. So we did experiment on brain imaging, and here is fMRI study. That's our old study in which we found that in humans particularly important is mirror, it means action and observation, inferior parietal lobe and premotor cortex. And this is a relatively recent meta-analysis which has been done by Carl Prinz and his co-worker. The group of Prinz in Europe probably is the best anatomy we have now in Europe. And he did this meta-analysis of 120 experiments in which they studied observation in humans, action observation in humans, and you see it's exactly the same region that I mentioned before also in the monkey. STS, which is a higher order visual area without motor components, than parietal. It's interesting that in human it increased, it's higher, it's larger. I don't know relative, I have not measured it relative brain, but anyway it's very large areas involved. But in evolution it has not changed. It's exactly the same part of the brain which are in the macaque monkey, so millions of years ago, so it developed for this social reason. Here it's a recent experiment in which also showed that in humans what it's called that it's the goal and not the movement, at least I will specify better later. So in this case it was something which was actually was asked for practical purpose to that. Sometimes the people who lost an arm have to use this artificial arm, and often they don't like it at all, so they don't like to have a prosthesis. So we were interested to see if observing with this prosthesis or it's the same or not in terms of brain activation. But for my purpose here, it shows that if you look in A and B, it's virtually the same activation. So when we observe grasping with the hand or with the instrument, we human being, it's exactly the same. However, in humans, you see this arrow below, there is a specific areas which then in Leuven they studied very carefully. It's specific for instrument. We also did an experiment in monkey which learned to use exactly the same instrument, but we have not found a specific area for use of tool. So when we observe, we human being, observe somebody using a tool, we have an activation which is unspecific and which is present also in the monkey, which means grasping or pushing, but then humans have kind of specific evolutionary area, new area from evolutionary point of view for use of tool. Now, a limit. I am not of those people who say, oh, we discovered mirror neurons, so we know everything about empathy and so on. There is strong limitation. And one limitation that was shown by this experiment, which we did in Italy a couple of years ago, and it's a very simple experiment. Imagine a student in a scanner. The students are in a scanner, and we present two series of stimuli. One, it's what you see here. It's something which is common to three species: biting. Human can bite, monkey can bite, and dog can bite. In the second part of the experiment, the same students were still lying in the scanner, but the stimuli were typically of each species. So the human was reading, it was a silent reading, so you can see only the lip moving. For monkey was lip smacking, affiliative gesture, and the dog was barking, again without sound. And the result was quite clear. So here is biting. That's something that we have and the animal have. We all know what it means, biting. If you look at the right part of the brain, right side of the figure, which is the left part of the brain, as a matter of fact, is identical. So we recognize biting of the dog with our, as if it was a person. We feel that that's something like me. On the right side, there are some small differences, but of course, because from visual point of view, the face of the monkey is different from the face of the dog and so on. But left hemisphere, which is the hemisphere which program action, is the same. Dog and me are the same thing. However, if we see now something specific to the species, it's completely different. Our motor system is strongly activated when we see reading. It's the Wernicke areas, Broca's areas, the classical circuit, including some motor part. For monkey, if you look, there is a strong visual activation, and then there is a tiny activation in correspondence of language area, of human language areas. For the dog, it's nothing. When we observe a dog, we have a visual stimulus, visual information, visual area become active, but we don't empathize with the dog. So if you think it makes sense, so we don't know what it means when the dog. We know scientifically the dog barks because he's happy or because he's angry. We can recognize from the sound, but we cannot bark. I can say, bow, bow, but that's imitation. It's inside myself, there's nothing. It's interesting that we make a debriefing of the student. You know, there is some activation in Broca's area, and monkey do not speak, do not talk with us. So what is that? So we asked a student, there are two categories. One was the most simple mind, they say probably has some food inside the mouth and she was moving. The other, the more intellectual group, said the monkey tried to communicate something to me. And so this attempt to receive this communication from the monkey was sufficient to activate the Broca's area in human. As a matter of fact, affiliative gesture, it's a communication gesture, so that they were in a sense right, but it's not for Broca's area to understand what the monkey was saying. Now, one point which somehow I feel a bit guilty, because from the very beginning, ethologists told me, Elisabetta and other people, Elisabetta Sagrandi, and other people told me, well, monkey do not imitate, so don't think about this neuron as imitation, but something maybe more at the basis, which precedes imitation, which is comprehension using. And so most of my research was in this direction. However, with Luciano Fadiga many years ago, we found that unlike monkey, humans also have a mirror system for intransitive gesture. So if I do a gesture like that, which means nothing, we thought about Greek letters or gamma or so on, but our students do not understand that, and yet we have an activation of the mirror system. In the monkey, we never found a neuron which fire if we just move the hand stupidly around. So humans have a specific way to code intransitive gesture. which probably was an evolutionary change from, at least from macaque monkey, I don't know about apes. But that's not simple. It has been stressed, especially by Ramachandra. If you have intransitive gesture, you can imitate in the proper sense. So in the proper sense, according, for example, to Tomasello, it's not just to reach the goal, that will be emulation, but to reach the goal using exactly the same way of acting as the teacher. So if you have to open an artificial fruit, for example, if you move like that, and then you move something, that you really imitate. So this is very simple for children to do that. Apes can do it, but with some difficulty, and monkey apparently cannot do. They just try to reach the goal. So what it means, that some species, and human in particular, are good for imitation. But that's not a minor point. Why? Because imitation is at the basis of our culture. It's not innovation. What is the basis is that we are able to imitate what the previous generation did. If we know that, we can replicate, and then some clever guy will be able to modify a bit and to find something else. But if we were unable to learn at school how to make basic geometry, we were unable to make a house. So all our culture is based on imitation, and probably the big difference between humans and other species is our great capacity to imitate and to transmit, so the imitation from generation to another. That has been demonstrated mostly by TM study, but I am not going to go into that. Now, what really rendered fascinating mirror neurons for most people, however, was another set of data, so that they are involved in social communication. That's our basic experiment, which we did in 2003 with emotion. That has been done with Christian Kaysen and Vittorio Gallese in Marseille. Why in France? In Marseille, there is a group of people which are very good in giving odorants. So to control odorants for a physiologist is very difficult because it's volatile, it goes around. But to control, so we did an experiment in which we gave to students different odors, different odorants. And some of them were pleasant, some unpleasant, some were neutral. But the experiment was really successful with those unpleasant. Rotten eggs, it's a wonderful stimulus. Everybody reacts in the same way, no problem. It could be a girl, it could be a boy, it could be anybody. So what happens that if we, here is the movie, now look here, that's in B. The red spots are the area, the small area, pieces of area, voxels, which are activated by unpleasant stimuli, by these rotten eggs. That's natural stimuli. I feel rotten eggs, my insula said rotten eggs, disgusting, and then I have all the behavior which is caused by this bad stimulus. The nice thing was that the one we showed faces showing disgust, we have the activation of exactly the same point. So there was overlap. The white spot is an overlap of my feeling of disgust and when I see somebody disgusted. So what it means? It means that I don't understand disgust because I think, oh, this guy is disgusted. No. I really feel to be disgusted. We are both disgusted. So it's sharing of the same emotion. So, few months later appeared a paper by a group of London, by Tanya Singer was the first author, but was also Priest involved, showing the same thing for pain. They showed that the experiment was done on girls, as a matter of fact. Somebody mentioned to me, on girls because they are more empathic, and so it was pain given to girls, and then they observed pain to their boyfriends, and it was exactly, they replicated our experiment fully. I mean, again, the same thing. So what it means that actually we participate, we share, we have a mechanism, a natural mechanism to share the emotion of others. Unfortunately, it has been already quoted, but I have already prepared it. That's Adam Smith from the Theory of Moral Sentiments. How selfish soever men may be supposed, they are evidently some principles in nature which interest him in the fortune of others. I think evolutionists, it's very important to be interested in the fortune of others. Maybe not so much in happiness, but certainly in pain, in disgust and so on, because from the evolutionary point of view, to understand that and to feel the same thing is very important for the group, for your behavior, and so on. Now, I want to show you also something. We move continuously from monkey to humans to monkey. So we want to learn something more about the insula, and with Fausto Caruana and Ahmed Jazini, a postdoc from Lebanon, we studied recently the insula in somehow unconventional way. So we used something which has been done in America by Graziano, prolonged stimulation, which were very popular 100 years ago. Well, it's been abandoned, but it's a very way to study it. So studying this insula in this way, we found, first of all, that insula is very heterogeneous. And there have been, for those who are in neuroscience, some crazy speculation about the insula, which is the site of consciousness, this mysterious concept, as yesterday has been said. Anyway, we recorded from the insula, and you see there is, in A, you see this strip going down. Well, this strip, it's very similar to somatosensory cortex. I will come back on this because it has very interesting implications for humans. The rostral part in B, that's with color, instead it's really motor. And it's very interesting what happens when you stimulate there. So I will show you because it's very telling. You must, this time there is no single neuron recording because it's stimulation. It appears a red light, and when it's red light, the monkey is stimulated electrically. You see the red light here. When the rat is stimulated, the monkey masticates. Now she stopped mastication. Stop. So we elicit, so it's a motor program for eating. So if you move just a few millimeters below, so not in the red spot, but in the blue spot in B, you will see now how changed the behavior of monkey. Red light. You recognize what is this grimace, which is common to us and other animals. Now she looks at it. Ah! Disgusting. No. So practically we have an area which is, first it's for positive eating, and the other is for negative eating. And negative eating is in the ventral part, and it's what produces disgust, which I showed you also in humans. And then we stimulate also the ventral part of the insula, which is, this part is really related to emotion, like the anterior part, but not the central in A. So this ventral part, now that's a bit more difficult. So you will see now Ahmad, who you will see it's a man with a big black bird, who will move his face towards the monkey. The monkey became angry. But if you stimulate this yellow part, appears lip smacking, which is a positive or at least affiliative gesture. So you will see it. Now Ahmad is straightening her, but if the light red, she became happy. Without light, she's angry. Angry. Maybe I will repeat so you will see better. So it's alternation between angry and happy. She's okay. Now she's angry. Look at the teeth. Now it's happy because the red light is on. So we can alternate it. So the insula have these motor programs which tell us what to do, but they are also related to what we call emotion, because in the moment in which you have this stimuli, you have what we call emotion. Now I will show you something recent which has been done by a Japanese, Ishida, in my lab. It's still in Japanese because he liked it like that. And you will see a mirror neurons in the insula. Now it's single neuron. Now monkey is grooming. Now it's this. And now will be the next part is the most interesting. Now it's another person. I don't know, it was clear. So it was the first part, it was touching him and grooming him, was a discharge. But in the last part, it was a girl grooming or trying to groom the head of my Japanese co-worker, and there was a discharge. So this neuron coded grooming done by the monkey, and one monkey observed in another person. Now to finish, let me go back to my slide. I will come back to this insula story, but before I want to say something about that. Some years ago, here there are many people who are interested in psychoanalysis and psychology. I have been stopped by Daniel Stern. Daniel Stern unfortunately died last year. He was a famous psychologist of development. And he said, why? Listen, you are studying what of the action. Sometimes you speak about intention, why. But in the real life, what is very important, it's how the action is done. I call it with vitality affect or vitality form, and this is in the way in which you communicate, this small gesture. So we did an experiment, not using very small gestures, but a bit exaggerated, but it was important for some reason. Now you see. So that's, obviously, it's a kind of communication, but be quiet, but it's kind. That's clearly there is some different feeling inside. And here is another example. This girl is very kind. This girl is not kind. So, but there is not the big emotion. That's not fear or angry. But this small, here it's a bit exaggerated, but in a normal life, continuously we recognize if the person is friendly or not friendly. If your girlfriend, it's okay with you, or today has a bad mood, from this small gesture. And according to Daniel Stern, in the relation between mother and kid, it's based mostly of this, even before language developed, on this small gesture. So we did an experiment in normal people, in normal developed people, and in autism. So that's, again, a fMRI experiment, and on the left side, you see the activation which are present when you instruct the person to look on how the action is done. In B, when you instruct the person to observe how the action is done. It seems very similar. As a matter of fact, there is more activation in A, because when you observe the finger, your resources are more involved. But what is extremely interesting is when you make a subtraction, forget about A, but look in B. In B, when you have this vitality form, you have an activation of a part of insula, which is exactly that part of insula which is not related to big emotion. So Daniel Stern many times wrote that this should not be considered together with emotion, but they are specific type of third behavior. We have emotional behavior, we have cold behavior, and we have this behavior which somehow is intermediate, which is the style of our relations. And the circuit apparently is completely different. It goes to a part of insula, and this part of insula, according to old literature, it's going back. It's not going to anterior part and then down for emotion, but it goes back towards the hippocampus, towards our memories, and so on. So I want to conclude with few words on one topic which we studied in these last years, autism. You know, autism is a disease which now is becoming almost epidemic. If you read the statistic, it increases tremendously. Then there are different explanations why it happened, because from the genetical point of view, it's nonsense. From genetical point of view, it's a disease on genetic basis, and autistic people have less children than non-autistic, so it should disappear. Instead, vice versa, it's increasing. So it's clear there is something not clear. But autism is very interesting because it has been explained first in psychoanalytic terms. It's kind of refusal of the kids, of the mother, of the world, and so on. Then it was very fashionable to think there is a kind related to theory of mind. So these kids are normal, but somehow are unable to understand in cognitive way the other people. And after 4 years, they started to do it and so on. But anyway, that was the explanation. One point which was completely forgotten was that practically all, I would say, all children with autism have motor deficit. And the motor deficits are present immediately. You can recognize, well, there are some form of autism which appear late, but anyway, in the classical autism, let's say, you can see this deficit very clearly from the very beginning. And already in the 90s, so motor stress there. But people say, well, that's by chance. 30% of autistic children have epilepsy, what has nothing to do, they are core deficit in communication and in language with that. But now we know that actually it's true that motor system is related. So now there is an enormous amount of study trying to see which are the motor deficit in autistic children and what is the relation. You know why it's very important? Because if you lose cognitive system, you can make a diagnosis when the kids are 2 years old, otherwise you can make a tremendous mistake. But if you look at the movement, at the type of pattern of movement, you can make diagnosis very early. And if you do early, apparently, I mean, the evidence is accumulating that the prognosis is much better, no comparison. If you initiate the rehabilitation with a very small child, it's completely different when you start at 5 years. The last experiment, we were very interested to see if children with autism has some deficit in this basic mechanism, which according to me precede the cognition. As I told you several times, I don't deny the cognition is very important. I showed you the experiment with the dog and so on, so it's clear that we have a capacity to mentalize. But look at this experiment. Here are kids which grasp a piece of chocolate and put in the mouth. And in the other part, he placed it into a container. We did a very low technology experiment, recorded the electromyography from this muscle. This muscle is the muscle which, with adults, open the mouth. So you see when the typically developing kids grasp an object to put in the mouth, red line, there is an activation of this muscle which precedes of 800 millisecond actual opening. So the intention is inside the brain, intruding and going as Lemon showed until the corticospinal tract, and you have this activation. Here is autistic children. He has difficulty to do that. Practically, he start to open the mouth when he has already chocolate in his heart. The normal kids start to initiate the opening, the mouth, the activation, much before. Kids only at the last moment. But the crucial thing is observation. Here is typically developed in children which observe another children eating, and you see the motor activity of the other go inside, intrude inside the brain of the kid and start to activate the myroideo muscle as if he was eating or she was eating. But here is autistic children, flat. This is high functioning. They understood completely what's going on. They were very attentive. They know, one of them is really very good in physics and mathematics. It's already in the beginning of the high school. And is unable to understand what the other is doing internally. He can say he's eating chocolate, but he's not in there. And recently we applied this our study on vitality form in autism. And again, it's a dramatic difference. For a normal kids, the task I showed you and that we use it in fMRI, it's very easy. They said it's, well, it's kind, it's not kind, but kids made a lot of mistakes, even with this very simple movie which I showed you. And the interesting thing that we have a group of young children, but another group was from 14 to 17, and nothing changed. Although they have a lot of social life, they have 17-year-old, still they have problem with this small sign, which indicate that their cognition is good, but their capacity, and in our normal life, you are not Sherlock Holmes when you are with your girlfriend. You are not thinking, oh, she's doing that maybe. You must immediately understand if she's kind with you or she's unhappy and so on. So this type of deficit is something which is extremely solid, and if you believe to these people who works with kids, this sign can be detected very easily and very early. So it opens some perspective on how to make the diagnosis of autism early. Well, thank you.